Okay, in this video we're going to look at this would be like an audio amplifier circuit, let's say, and this is a very common configuration for one. And in particular what we're going to see is how does this circuit respond to a voltage source which actually has two components at two different frequencies. One of those components is at 0 hertz, the other is at some frequency omega right here, right? So this is a linear circuit, right, LTI. The way to solve it, right, is to solve it at both frequencies and then sum it together at the end. And we'll actually see this one isn't too bad when you actually do out all of the math, right? So for example, if we, so let's first of all, let's solve it at 6 volts, okay? Or I'm sorry, at omega equals 0. I'm going to redraw the circuit at that point just so we can get an idea of what's going on there. Cool. Go away. Okay, good. So when omega is 0, right, that we're going to analyze the circuit at that point. The voltage is only 6 volts, okay? And then what we need to do is, this is a classic inverting amplifier topology. We can do it exactly the same as we've always done it, right? We have one impedance and another impedance. So really, and then the output is just an 8 ohm resistor. And as we know with op amps, right, one of the reasons we use them is we actually don't need to worry about output loads with them because they will provide whatever current is necessary to keep the voltage at what they specify. So this is kind of a misdirection in terms of solving. We don't need to worry about it. The reason I put it in here, though, is because oftentimes 8 ohms is a very common speaker coil resistance. So in this situation, we're putting in a audio signal with an offset, we would call it. And this goes into here, and this capacitor will see its purpose in a second. But then there's some amplification based off of these, and then we can drive our 8 ohm speaker very nicely. But anyways, back to our first solve at omega equals 0. We need to analyze the circuit at omega is 0. So what does stuff look like? Now the general form would be that there is this impedance, right? Let's call it Z1, and then there's this impedance, Z2. Okay? And then your output of your op amp will equal whatever your input is times, and then these are in phasor form in AC, Z2 negative over Z1, right? This is exactly the same as an inverting amplifier from before where it's negative R2 over R1, right? This is also, let's just assume it's an ideal op amp and all of that stuff. But whatever. So if we look at this in DC, right, we don't even need to necessarily come up with the whole 1 over j omega c stuff, right? What is a capacitor in DC? It's open, right? So what ends up happening is this effective impedance is infinite, right? It's 1 over an open, I'm sorry, it's an open plus some finite value, which this in series impedances, the larger one dominates. So it's actually going to end up being negative R2 over infinity, and I know that's not 100% mathematically robust to write that, but whatever. So this is basically 0. So this is saying the DC gain of this circuit is 0. All right, so any DC amount, any omega of 0 amount coming in is going to not show up here. Now let's look at it at omega being not 0. So I'm going to copy it down there again. Okay, so same situation. We have Z1, let's call it, and Z2. Whoops. Okay, good. So Z1 will equal 1 over j omega c plus R1, and Z2 will equal R2. V out here, let's call this V out, sorry about that. V out, phasor. And then this is, sorry, right up here, let's do 3 volts cosine omega t. But V out will just equal negative, again, Z2 over Z1 times whatever the input was. So in all of these particular cases, it'll be negative R2 over R1 plus 1 over j omega c times, and if we're in complex domain, it's just going to be just 3 volts, right? Yep. Because there's no phase on that. Cool. Now, what is this going to look like again? This will be, I don't like the j omega c in the bottom here, so I'm going to multiply the top and bottom by that, so it'll actually be negative R2. Let me rewrite that a little bit. Negative j omega c R2 over 1 plus j omega c R1. Great. Times 3 volts. So then V out, of course, equals that. If we really wanted to think about like magnitude and phase of all of this, right, we could. So just for the sake of doing it out, I'm going to actually break this into its magnitude and phase components, right? So the phase of this will equal what? So the top right here is going to have actually a phase of negative pi over 2 all the time, right? It's a purely imaginary thing. So this is always going to be negative pi over 2, right? And then what's the bottom phase going to be? That's actually going to be minus whatever this ends up working out to be. And that would be a tan of omega CR1 over 1. And if we analyze, if we just think of the limits here, right, as omega goes very, very big, this is going to go to a very, very large imaginary part compared to a very small real part. So this will go towards 90. So your phi on this will just end up being ranging from anywhere from negative pi over 2 to negative pi total, right? Because this is negative, or this will be pi over 2 as well. Then your magnitude, on the other hand, is going to be what? This will just equal 3 volts, right? And then times, so the magnitude of the top part is just going to be square root of this thing squared, right? Of the imaginary part, so I don't even need the j omegas in there, sorry about that. Omega. And then square root of 1 squared plus omega CR1, sorry, that was an R2. Yeah, this is, I mean, this is fine enough for, I think, our purposes. So if we needed to write this out and come up with a function, like, you know, as a function of time, we would say V out as a function of time will equal this mess, 3 volts times, obviously squared, this is just omega C R2 over square root of 1 squared plus omega C R1 squared times cosine of omega t minus pi over 2 minus a tan, whoops, cool, right here. Now you'll notice, right, this function is only a function of the omega t's, like the non-DC values, right? So if we scroll up here, right, whenever we analyze it at DC, we actually found out that the gain was 0. Whereas if we analyze it when the omega, when we're not in DC, when omega is anything else, we will get some fraction of signal through. If we analyze this equation at omega is 0, what do we end up with? We end up with 0 in the top. So this actually evaluates, this is a good sanity check, right? But at omega equals 0, this thing equals 0 as well, right? That's good. Because that sort of agrees with our initial at omega is 0 analysis. But what's going on here, right? Like, what is the purpose of this capacitor? Well, it does provide some filtering, and that's good to understand. But more importantly, this is what we call a DC blocking capacitor. So a lot of times signals come in not just on their own. So maybe like this is an audio signal, right? And omega can be a whole bunch of different omegas. You have to analyze this from all those frequencies. But this sort of represents an audio signal coming in, a time varying voltage. But then oftentimes they come in with what we would call a DC offset. And we want to avoid putting that DC offset into a speaker, because actually speakers will like heat up and catch on fire if you provide just DC through them, because they have such a low resistance. And so what we want to do is we basically only apply the gain to the non-DC components, and everything else, so any sort of DC element of it, so the 6 volts never makes it through here and doesn't show up on the 8 ohms or get amplified by the R2-R1 ratio. Instead, only things that actually vary in time pass through it. And they will pass through it with differing amounts, because this does end up, this is a function of omega, and you could actually plot this out over time, I mean over frequency, right? And, you know, if this is omega, right, we could come up with some sort of magnitude plot and phase plot as well. We're not going to worry about that here, right, but that would actually matter. It just so happens usually they'll make like rather large capacitors here, because the larger the capacitor, the lower the cutoff frequency, and the larger of a window of AC signals it'll pass.